It is yours.
Hello.
Slides are there. Okay.
Hi, Marcos. I hope you can hear me. Just checking if
Yep,
everything is okay. Perfect.
everything's good.
Okay, if you can see my screen, then I will start.
We
Very
can see
good.
your slides. Yep.
Perfect. Let me just get the thing out of the way. Okay. Hello, everyone. Welcome to this talk. I'm covering ESA's LEO-PNT in orbit demonstration mission and the future. So like Marcos kindly introduced me, I'm Sarnadas. I'm a radio navigation engineer at the European Space Agency based in the Netherlands. Very happy to be giving this talk today on behalf of my colleagues from the ESA's LEO-PNT project team. So before I begin, just thanking again Professor Marcus and the IEEE LEOSATS community for the kind invitation and for the opportunity to present and discuss the LEO-PNT with such a distinct group of speakers in our audience. So without further delay, let's begin. So satellite-based navigation, or SatNav as we used to call it, represents the largest spin-off of space applications with more than 6 billion users all over the world. In Europe, roughly 10% of the EU GDP relies on these systems, with an ever-increasing downstream market and further proven with its flagship GNSS system, which is Galileo, and its space-based GNSS augmentation system, which is EGNOS. This massification of the SatNav use brought increased user appetite for more and more position navigation and timing, or PNT, services as a commodity. This is coupled with demands for increased accuracy, availability, and efficiency. But this dependency on GNSS is not without challenges and risks, as we all know. One example being the increasing number of reported jamming and spoofing incidents, which you can see a small illustration on the slide on the right. Today, it is clear to the international community that the single positioning system is not enough to meet the current and future user needs. So what are the prospects of evolution scenarios for satellite-based navigation systems? From the recent evolutions, we can anticipate a new paradigm in the form of this layered PNT system of systems concept, where GNSS acts as a global backbone, which we call the layer 1, a second layer at the lower Earth orbit, providing PNT diverse services in complement and or addition to GNSS, depicted as layer 2, then we can have a number of local and regional components used to complement the satellite-based navigation in challenging environments, such as urban areas, where local infrastructure is available, which is layer 3. And finally, multiple sensors can help users navigate during short outages of SatNav and or the terrestrial networks, providing additional absolute or relative measurements and improved situational awareness, which is captured here as layer 4 at the user equipment level. So today, I will be focusing the attention on ESA's perspective on the realization of this layer 2 for LEO-PNT service provision. Of course, as this workshop also demonstrated, and is already illustrated in the presentation before mine, we are by far not alone in this LEO-PNT landscape. There are several initiatives that recently came to life worldwide, both at institutional and commercial levels, proving that LEO-PNT continues to be a promising way forward. Regular workshops and meetings are now organized at international level as well. For example, under the United Nations International Committee on GNSS, the ICG, to foster dialogue and cooperation among all actors and ensure interoperability and compatibility of the different LEO-PNT concepts and realizations. So all this together brings us to the consolidated concept of the multi-layer system of systems, where LEO-PNT is expected to play a fundamental role. This concept is quickly becoming a reality. Not only this workshop is proof of that, but such reality is also backed by the institutional and governmental plans. One example is the materialization of the LEO-PNT concepts as captured in the latest radio navigation plan from the European Commission, which is shown in the top left, among many others as comprehensively captured in the LEO-PNT State of the Market report from Frontier SI that I just presented before, which is captured there on the top right. Now let's go a bit deeper on some of the LEO-PNT benefits and differentiators. We start with the frequency diversity. Considering the LEO-PNT as a blank canvas where we can provide LEO-PNT services, there is an opportunity to expand this service provision to other frequencies besides the GNSS L-band. In fact, some GNSS providers are already exploiting S-band carriers, and one can consider LEO-PNT as going both lower and higher in frequency with different objectives. We will address the details on the frequency diversity in the next few slides. Going clockwise, we now highlight some of the benefits of the lower orbits. On one hand, the satellites are closer to the users, allowing for lower path losses, for potential increases in received signal power when compared to GNSS, and for provision of two-way services. On the other hand, the LEO satellite's own orbit termination and time synchronization, or ODTS process, can be executed on board the satellite itself and alleviating the need for massive deployment of tracking, monitoring, and control stations on ground. Therefore, these factors reduce complexity of not only the satellite platform, but also of the ground segment. The LEO-PNT also opens new possibilities for PNT service provision. Together with new frequencies, wider bandwidths, and more tailored signals, users can anticipate newer and better services, for example, in emergency situations, first responders, critical infrastructure, timing, situational awareness, or integrity. Additionally, some of these services may still reach users under challenged environments, such as in deep urban scenarios or even indoors. Finally, the exploitation of LEO-PNT geometry and dynamics can play a significant role in improving the overall PNT performance, in particular for what concerns precision applications or multipath mitigation. Let's go into this a bit more in the next slide. So what is there to gain from the exploitation of LEO-PNT's geometry, its dynamics, and the resulting measurement diversity? First, the higher velocity of the LEO satellites can be leveraged to decorrelate measurements and assist the PVT algorithms in apportioning and estimating error contributions in a faster way, leading to reduced convergence times for PVP algorithms using GNSS and LEO measurements. This is illustrated with a simulation example at the bottom right plot, where we can see that combining LEO measurements with GNSS can reduce the overall PVP convergence times to a few tens of seconds. In urban or multipath-prone scenarios, the faster dynamics of LEO satellites introduce faster changes in geometry, and especially in line-of-sight conditions, which can help with faster measurement decorrelation and mitigating multipath. Other exploitations of LEO satellite measurements, such as the ones used in opportunistic approaches, can also bring added value, examples being the techniques based on Doppler positioning or the use of the additional measurements as source of redundancy or coasting during outages. Now let's illustrate this with one example of a PVT user in a simulated urban scenario, including GNSS satellites from the nominal Galileo constellation, as well as LEO satellites, which are introduced here in the scenario as a small constellation of 60 satellites in polar orbits. In this simulation, the stars represent Galileo satellites, and the circles represent LEO-PNT satellites. Green means in view in direct line of sight, while the red means obstructed. Finally, a position fix is considered valid if the geometric delusion of precision, or GDOP, is below 10, which represents a moderate impact on PVT accuracy. So, as we began, we can see that the only PVT available is the one combining LEO and Galileo measurements, given the reduced satellite visibility. This means that no standalone PVT solution is possible, neither with GNSS nor with LEO alone. At some instances, the PVT availability is interrupted, although it may be quickly recovered in a few seconds. These gaps in the PVT solution, if short enough, can still be mitigated with some degree of propagation with the help of inertial measurements. In some periods, we can also observe at least 4 LEO satellites simultaneously, which allows the receiver to compute a position solution using only LEO-PNT measurements. We also see a reduction of the GDOP for the combined solution, as we now have more Galileo and LEO satellites in view, resulting in better geometry. At last, we eventually observe a PVT solution based only on Galileo with 4 satellites in view, which happens roughly after 15 minutes of scenario. It is noted that this time is only indicative for one GNSS constellation and could be less with multi-constellation scenarios, but it's still representative of the impact of a slower changing geometry in situations of less visibility. Now, as mentioned before, LEO-PNT brings opportunities for new frequency bands that can help address the many improvements required by the user, such as accuracy, integrity, and resilience. For example, while going to lower frequencies could allow some level of indoor penetration, staying within the L band could ease current user adoption and improve service provision in existing bands. And going to higher frequencies, such as the C band, could enable better signal-in-space transmission by exploring wider bandwidths as well as the lower ionosphere propagation impairments. The table at the bottom left of the slide identifies a quantitative exercise as a contribution to ESA's proposal of frequencies and bands to explore in its LEO-PNT in-orbit demonstration mission. The exercise is a trade-off in potentially available frequency bands and bandwidths for radio navigation satellite services, and the impact on performances, on user equipment adoption, on signal design and data rates, or in technology maturity, among many other factors. Resulting from this exercise, one clear case that highlights the potential of LEO-PNT to go beyond current GNSS allocations is the opportunity to extend the current RNSS C-band allocation up to 240 MHz of bandwidth, while still complying with international regulation concerning power flux density limits. Looking a bit more in detail to ESA's LEO-PNT vision, we start with the identification of three main strategic pillars for LEO-PNT. The first pillar relates to resilience and robustness. The idea is to exploit the new frequency bands and two-way links to improve the resilience of the PNT service against threats such as jamming and spoofing. The second pillar is linked to augmentation of European GNSS, namely Galileo and EGNOS. On one hand, to improve the overall performances and precise positioning in urban environments and in data dissemination channels, and on the other hand, to augment Europe's GNSS capabilities by monitoring Galileo and EGNOS signals from space, supporting integrity concepts and boosting inter-system connectivity. The third pillar focuses on the provision of new services exploiting new signals. The first being a non-terrestrial network or NTN 6G signal to provide PNT services to smartphones supporting these signals without extra cost for the terminal. As an example, the service can be exploited for personal emergency or low-energy PNT. The second being the use of UHF and VHF bands and dedicated PNT signals for indoor positioning or timing service provision. All this brings us to ESA's ongoing LEO-PNT in-orbit demonstration mission. With the objective of demonstrating LEO-PNT concepts and services while maturing and de-risking European key technologies and user adoption, ESA has initiated in 2024 a fast-track LEO-PNT in-orbit demonstration under ESA's FutureNav program framework. The LEO-PNT IOD contracts have been kicked off in early 2024 and are well underway. Soon after the first launch, the IOD will include experimentations and service demonstration campaigns to showcase and validate the most critical technologies features of LEO-PNT. And in the long run, this IOD mission will also support the preparation of future operational LEO-PNT systems. The LEO-PNT IOD is being developed under two parallel contracts, both with large and multifaceted consortia. One prime is GMV in Spain, and the other prime is Thales Alenia Space in France. Each of the contracts include all aspects of the IOD, from the space segment and satellite development to launch service, ground segment, operations, to the test user segment, experimentation, and service demonstration. The IOD is split in two deployment targets and objectives, the same for both consortia. The first step is a single Pathfinder A satellite, with a subset of PNT payload capabilities at L and S band only, and with the main objective of de-risking the critical technologies and demonstrating the first capabilities with one satellite experiments. These satellites will be deployed in a quasi-polar orbit at approximately 550 kilometers altitude and ensure a lifetime of around 12 months. Both Pathfinder A are targeted for launch readiness by end of this year. The second step is a set of 4 Pathfinder B satellites expected to begin launching around the end of 2026. They will be launched in similar orbits as the Pathfinder A, but will now be bigger and include the full PNT payload capabilities. These Pathfinder B satellites will be deployed as a mini constellation to be used for the complete LEO-PNT experimentation and service demonstration activities to be run at least until the end of 2027. Going a bit more in detail with the IOD space segment, we see here both Pathfinder A satellites. They will be 12U and 16U CubeSats respectively, weighing between 20 and 30 kilos. Some differences in the platforms include chemical versus electrical propulsion or the units for altitude determination and control systems, the ADCS units. As for the payload, they will be very similar in terms of capabilities, including onboard GNSS receiver and ODTS and the PNT payload for L and S band signals. One example difference is the L-band transmit antenna, one being a patch antenna and the other a quadrifilar helix antenna. Under the GMV contract, the Pathfinder Ray development is led by Allen Space in Spain, and under TASEF contract, the Pathfinder Ray is led by German Orbital Systems in Germany. As for Pathfinder B satellites, they will be similar in specifications, as they both are targeting the same PNT payload capabilities and the same signal in space ICD. On top of all capabilities in terms of payload already discussed for Pathfinder A, the Pathfinder B satellites will now include all bands and signals in UHF, L, S, and C bands, as well as two-way service capability. In addition, other payload capabilities may be exploited, for example, as proposed and defined per each contract. All Pathfinder B satellites will have a mass under 100 kilos and a lifetime of at least 36 months. The target is that they will be deployed as 2 satellites per plane in nearby orbital planes, with the objective of having experimentation windows with the 4 Pathfinder B in view, at least for each contract. Under GMV contract, the Pathfinder B development is led by OHB in Germany, and under TASF contract, it is led by Thales Italy together with Demos in Spain. Now, with one of the key factors of LEO-PNT being its capability to perform ODTS on board the satellites, while directly receiving and using GNSS signals from the NEO satellites, the LEO-PNT IoT ground segment will be a lean service-based deployment. Anyway, the ground segment is still of paramount importance for all monitoring and control of the LEO-PNT satellites and their operations, including during launch and early orbit phase, in-orbit testing, routine operations, or any other required special operations like station keeping or collision avoidance maneuvers. The ground segment will also be responsible for receiving mission data and providing the several products to support the IOD and experimentations, especially towards the test user segment. This user segment is the main responsible for enabling the IOD experimentation and the service demonstration by implementing several realizations of receiver chains. Multiple user equipment types are realized, they are called UE breadboards, to support experimentation and validate the reception and processing of LEO-PNT signals in representative terminals. A reference test user receiver and transmitter for LEO-PNT, called Turtle, is developed in each consortium to further sustain the experiments and validations, both in real-time and post-processing, and capable to process all bands, all signals, all services in multiple configurations for computing reference, benchmark, and figures of merit. The test user segment in its constituent blocks will be deployed and exercised in multiple locations, operating with real signals as soon as the first Pathfinder A is transmitting in orbit, and will remain in continuous support of all the IOD experiments and demonstrations with all the Pathfinder A and B satellites for the coming years. Now, as expected, the main goal of the IOD are to demonstrate the LEO-PNT capabilities, the benefits and performances, as well as to exercise and showcase a multitude of user cases where LEO-PNT can be exploited to the benefit of different users. For all these reasons, ESA's LEO-PNT IOD will include an extensive experimentation campaign under the responsibility of each consortium to extensively cover use cases, concepts of operations, and user processing capabilities with LEO-PNT signals and services, both standalone and under the multi-layer concept. The first set of experimentation starts already with the Pathfinder A, focusing on extracting indicators on ODTS and ranging accuracies, demonstrating the payload performances, and validating all nav signals and data transmission and reception chains. A reduced number of use cases can also be explored with one satellite in view, such as some Doppler positioning, timing applications, or GNSS plus LEO joint processing. Then, with the deployment of the Pathfinder B satellites up to the 4 satellites in view, the experimentation will be extended to demonstrate the LEO-PNT service provision and performances for standalone and hybrid PVT, PVP convergence times, accuracy, resilience, and different service demonstration under representative use cases. For example, static, dynamic, automotive, maritime, urban, handheld, critical infrastructure, and among many others, and with the involvement of the end users themselves. But ESA's LEO-PNT will not stop at the in-orbit demonstration. In fact, it's actually just the beginning. As introduced before, ESA and its European Union partners are already developing efforts towards an EU institutional LEO-PNT operational system while also supporting commercial initiatives. The extensive work already performed by ESA's LEO-PNT team and all the industry partners, and the results still to come within the IOD, will keep providing valuable inputs towards the future LEO-PNT operational system. And for this reality to materialize, we will enter an in-orbit preparatory phase. ESA's Ministerial Council of 2022 put already in motion the LEO-PNT in-orbit demonstration, while also cementing the vision for the future. This vision is now under consolidation in the context of the next Ministerial Council of ESA, scheduled for November 2025, which marks the launch of the in-orbit preparatory phase with all its industrialization and IOV flavors. This development of industrialized building blocks for production at scale to allow boosting production and deployment rates and decreasing risks and costs is also expected to cross-fertilize towards a number of LEO-PNT system engineering activities developed under EU's multi-year framework. By the time of the following rounds of ministerial councils and financial framework consolidations, which will happen around 2028, the LEO-PNT landscape may evolve towards a deployment and exploitation phase, with the first LEO-PNT service capabilities reaching an operational state. Now, going a bit deeper on the industrialization steps, it is our objective to support and sustain a product-oriented approach to the development and demonstration of the building blocks. To do so, we aim at fostering the inclusion of modern and innovative processes and techniques for manufacturing, testing, demonstration, and qualification of the building blocks, bringing them to the required reliability and maturity. Examples of these building blocks are low size, weight, and power payload modules, front ends, high power amplifiers, filters, clocks, clock control, onboard ODTS, antennas, intersatellite links, or user-receiver chipsets. For satellite platforms, the program will leverage on the European and national initiatives already maturing all across Europe. And for this, ESA has already launched a request for information in early 2025 related to the industrialization of LEO-PNT building blocks and in-orbit validation of space segment aspects. Now, this slide illustrates a bit how the LEO-PNT IOPP could look like. So several LEO-PNT satellites embarking these building blocks and payloads are making up the space segment, potentially expanded with inter-satellite link connectivity. The signals in space would include all candidate frequencies, all signals and services towards the test user segment. Then, a ground segment is deployed to manage the constellation and mission operations, while IOV testbeds sustain the validation chain of activities and data flows, avoiding any disruption of the operational systems and services, allowing them to coexist. Now, to conclude, a few takeaways. A LEO layer for PNT is a promising opportunity to improve GNSS resilience and robustness, improve GNSS performance, and provide new services as part of a multi-layer system of systems concept. ESA is fostering the European LEO-PNT ecosystem through the Future NAV program, starting with the ongoing LEO-PNT in-orbit demonstration with its two parallel contracts. The ongoing in-orbit demonstration mission means that 10 IOD satellites will be launched within the next 3 years, all supporting a common signal in space ICD. Opportunities for future operational systems are under investigation and discussion from both institutional and commercial perspectives, and in coordination with European Union stakeholders. The subsequent phases for LEO-PNT in-orbit preparatory phase, including the industrialization and the in-orbit validation, are on the table and are moving forward. So with this, I finish my talk for today. Thank you again for the audience for your attention, and thank you all to all the speakers and the organizers, and I wish everyone a very fruitful workshop.
Hey, so thank you so much, Rui, for sharing the details of the ESA PNT, LEO-PNT mission with us. We received a couple of questions in the chat and the Q&A box. So let's start with the first one. Can you also outline how LEO-PNT is used or might be used in space situational awareness? So any topics you are working with in that domain?
Yes, thank you. So indeed, LEO-PNT can help in that regard. Well, in many ways, there's one situation of, like we discussed before, of augmenting in this case, the European GNSSs like Galileo and EGNOS, where the LEO layer can already be acting as a monitoring station in space. And this can be extended further with the use of the inter-satellite link connectivity. So if you have kind of a mega constellation, or at least a large constellation at the LEO altitude, it can be leveraged to also improve the situational awareness, not only from what happens in GNSS, but also from the monitoring of the ground, and to communicate this through all the constellation of the ground segment by using also the inter-satellite link.
Mm-hmm. Okay, thank you. Then we received another question, which was the 17 megahertz S-band. Is the RNSS one, or did you ask for an MSS, so mobile satellite service band, to ITU? In the second case, is it already allocated, the band?
So to start from the end, in terms of bands, allocation of bands, so both consortiums are responsible for doing the filing, the frequency filings and discussion for the IOD. So this is underway. They are being discussed. In terms of ICD, I can say that they are both considered, the RNSS allocation and the MSS allocation as well. There are different opportunities to exercise S-band signals, more radio navigation-like, or more SATCOM-like, if you will, or communication-like, if you will. So they are both on the table for the IOD. Again, as an IOD entails, there will be demonstration of different working points and different opportunities to exercise these bands.
Great. Okay, thank you.